Watchtower.
Okay.
Oh, so yeah.
Because they have to do an assignment.
All right, everybody. Maybe we'll start up here. So we're pleased to welcome Dr. Benham Jafapour. I hope I'm saying that correct. Yeah,
recording in progress.
To visit us. So he's, as you know, we've been interviewing lots of candidates the past month. Dr. Jafapour and his wife are actually opportunity hires. So UT Dallas and UT Southwestern are trying very hard to hire them, and I think other people are too. And so we have an opportunity to have him visit our department, and the usual thing, everybody can meet with him and have a little bite to eat with them and discuss with them. And then tomorrow I'll ask your feedback from everybody, just in the usual way. So anyway, we're very pleased to have you here and hear about some of your work. So I'm gonna give a brief introduction. I can't possibly cover all the material, but I'm gonna give you a brief introduction. So Dr. Jafapour has his PhD in civil environmental engineering at MIT, which I understand is a pretty good school, I think, isn't it?
They say so.
Yeah, right, they think so. It is. He's also got various degrees in electrical engineering and civil and environmental engineering from MIT, Delaware, in his home country of Tehran. Of Iran, the University of Tehran, and he's been at several universities, appointed at several universities, but most recently, and I think for the longest period of time, at University of Southern California, USC, which, funny enough, I used to teach there some years ago, maybe 20 now, a while ago anyway, and he's in the mechanical engineering, and also co-director of a research center there, very active research center. And I would say, I mean, you're involved in a lot of different things, which is interesting and exciting, but maybe the key thing is centered around fluid flow of various types, computational and other aspects of fluid flow. And that can apply to reservoirs, aquifers, CCS, geothermal, et cetera. So I think we're going to hear a little bit about that today. And I think we're recording, is that right, Saloa?
Yep, we're recording.
Yeah, I don't see it. Yeah. Okay, it was. Yeah. All right. So with that, we'll let you begin, and we look forward to your talk.
Thank you so much. Thanks everyone for coming to my presentation. It's a distinct pleasure to be here to share with you some of the work that we do in our lab. And the name of our lab is Subsurface Energy and Environmental Systems, and it's intentionally named so. I will go through a few slides at the beginning to introduce what kind of work we do and what is the motivation behind the work that we do. The main topic for today's presentation is going to be dynamic characterization of the subsurface flow systems using. More recently, our focus has been on deep learning architecture in order to advance subsurface characterization using dynamic data. So this is a picture that from the Department of Energy showing some of the key resources, energy and environmental resources that we have in the subsurface environment. And basically the traditional oil and gas, obvious source of energy, geothermal reservoirs, and CO2 storage. There are other applications in here that, but the main focus for us are these three. This part is we have conventional resources, and we have unconventional resources, and we have projects on both. Now, in order to introduce the focus of our work and what we're trying to do and how we are trying to approach the problem, what I'm showing in here is a computer simulation model. That the purpose is to simulate flow and transport in this system. And by the way, that's the fundamental underlying common challenge in those applications. because if we know how flow and transport happen in this system, then we know how to control this system. And if we know how to control this system, then we would try to optimize the performance. That's basically the idea. But it's not easy. It's very challenging because we don't have access to this system. We have very limited access to either drilling, very costly, or we do have through geophysical monitoring techniques, we do have lower resolution data, but rather high coverage data that we can use to monitor the system and learn about their behavior. For basically research trust in my lab are characterization of this system in an effective way, dynamic monitoring and using dynamic monitoring to inform this characterization, uncertainty quantification, which is a significant challenge when we deal with subsurface in general, and of course when we want to simulate flow and transport. And finally, all of this is done in order to optimize energy recovery performance. We want to be able to predict the behavior of the system so that we can optimize the performance. Now, so let's take a look at some applications that I've already shown that we focus on in our lab. In energy systems, geothermal, conventional reservoirs, unconventional reservoirs that I named. We also have environmental systems. And in our case, the environmental application we focus on are really related to energy recovery. And those are geological CO2 storage. That's one of the topics that we've been investigating in the past 10 years or so. Some of the risks involved in energy production, induced seismicity, and also related to geologic CO2 storage, issues related to leakage and minimizing basically leakage from these formations. And then, of course, there are groundwater systems, and most of what we focus on is really their contamination through some of these activities, including and mainly for CO2 storage. So these are the applications that we focus on. Now, in terms of technology, this is pretty much the two technologies that we focus on are data science and system science. So with understanding of flow and transport processes, of course, that's a domain knowledge, we bring in data science and system science in order to develop technology that would help us with that goal of being able to characterize and control the system. Right? And that's the purpose of, that's the vision in our lab. And this is like basically the snapshot of everything that we do. Now, as I mentioned, this is another way to look at it. These are different applications that we have in energy and environmental system in subsurface, where we actually bring data science and system science in order to be able to do management and optimization of these resources. Now, with this is the last slide in terms of introducing what we do, and then I move on to the main topic of the presentation. So this is a flow simulation model, and what we see on the right-hand side is a systems approach toward managing any of these applications, whether it's a geothermal reservoir or CO2 storage or a oil and gas reservoir. The fundamentals remain the same, at least the way we want to approach this problem. So what I'm showing on the top part is the physical system itself. This is the subsurface that basically the flow and transport that is taking place in this system. Now, what we do, we usually have some control inputs into this system, and we do have measurement sensors that we measure the feedback based on what we do, how we operate in the field. What you see in the blue is basically our modeling activity to represent approximately what is happening in the reservoir itself, in that formation itself. But of course, this is not perfect. This is based on very limited data, but a lot of work goes into, a lot of expertise goes into building these kind of models. But once we are ready to use this model to predict how the system behaves, we are going to see almost certainly that our predictions don't match what we see in the field. And that brings us to two continuous loops that I'm showing with green and red. The green loop is what we call model update, which means that if you see discrepancy between your predictions and what you observe in the field, you want to address that. And that's done by updating your model. the focus of today's presentation would be this loop. But there is another loop which is attached to it. And of course, every time you change your prediction or your model, you have to also change your decision. Or you have to look into the possibility of needing to change your decisions, which means that you have an optimization framework attached to these models. Once the models are updated, your optimization and decision how to control your system is going to have to change, right? And that's basically the overall work that we do in terms of characterizing and managing subsurface solution systems. But the key idea here, you can only do this optimization if you do have reliable models and reliable predictions. So the four areas of research that I showed, description and characterization of complex geosystems. And I'll talk a little bit about that today. The idea here is that how can we affect, these are very high dimensional models. And what you see me talking about after this slide is how do we have a compact representation for these? Because we have very limited data. In terms of data content, we are very limited. How do you update large, high-resolution models with limited data? So we have to kind of address that imbalance in terms of resolution. So this is the second part, which is dynamic characterization and uncertainty quantification. These two in our lab used to go hand in hand. You basically do effective characterization, so you can do efficient updates to your model. And then the third area is field development optimization. And in the past, we have focused on performance optimization for energy recovery. More recently, we have used optimization frameworks to address environmental issues to minimize the risks of, say, use seismicity or large deformation that might happen. And for that, I work with people who do geomechanical simulation, coupled for geomechanical simulation. And then finally, more recently, we have focused on data science and for prediction and decision support, trying to tap into some of the potential that exists in recent advances in data science to improve some of our workflows. So with that introduction to my group, now I would like to basically tell you what I'm going to talk about for today. A very brief introduction to subsurface flow systems for those of you who may not know the basics about subsurface flow. Then from there, I move on to the dynamic characterization, which also known as an inverse problem. So sometimes you see me referring to it as an inverse problem, sometimes dynamic characterization problem. There are other names also for it, but I limit myself to do those. And then I'll talk about the challenges. What are the main challenges when you approach a problem like this? And after that, I talk about the need for parameterizing with lower rank representation to be able to have a meaningful update to these models that we have. And then the last two areas that you see in here would be some of the recent approaches that we have developed in order to deal with this low-dimensional representation or dimensionality reduction problem, and looking at some results from inverse modeling after developing these techniques for low-dimensional representation. And lastly, I'll talk about briefly some of the ongoing research in other areas that we have. Okay, so subsurface flow. I have probably one or two slides to give you a summary of the key aspects that are relevant to my talk. The physics of it, typically the flow and transport in subsurface is governed by conservation principles, a combination of mass balance, momentum balance, sometimes depending on what application you have energy balance, which typically lead to a set of partial differential equations that needs to be solved. What is important is that for our work is that some of the key parameters that really impact the solution of these PDEs and the behavior of these systems are the underlying properties of rocks and fluids and their interactions in these formations. And the prediction accuracy depends on the quality of those input parameters, which is really the central to the topic of today's presentation. You can have the best or most perfect physics that you want to simulate, but if your input parameters are not accurate, you're not going to get the response that you're looking for or that you see in the field. So these parameters are extremely important, and our goal would be how we can actually improve the description of these parameters using dynamic data or feedback we get from the field. And then the solution of these systems, one of the challenges in simulating the response of this system is that these are very large, complex models and computationally very expensive to run numerical simulation for these models. Given that, some of the workflows we develop will be affected by that computational complexity. And that's where we try to also develop efficient, approximate tools for forecasting, which will make these workflows more practical. All right, so in this slide, what we see is, as I said, there's a lot of effort that goes, geophysicists, geologists, and reservoir engineers work together in order to, for this part of it, mainly geophysicists and geologists, to put together what we call a subsurface flow model. You can call it a reservoir model, you can call it an earth model. But the idea is you have, based on the static data that we have collected and the expertise and interpolation schemes that we have, we put together one or a bunch of models that we believe are consistent with the data that we have up to that point. Now we begin the production from these fields, energy production from these fields, and we begin to observe responses from these models, from these fields, and we predict those responses also with our models, and we see discrepancies almost all the time at the beginning, especially at the early stage of the field production, because there isn't a lot of feedback yet from the formation of the reservoir. Now, at that point, you have to kind of look at how you can address this discrepancy, and that problem is challenging. And I will go through some of the challenges that we have to deal with in doing this kind of model updating. So continuously updating subsurface flow model using monitoring data. That's what we aim to do. So this slide is showing the forward problem that I talked about so far, which is you build a model, you use that model as an input to basically a reservoir simulation model or software to solve this PDE equation with some of the inputs coming from, input parameters coming from this model. Permeability, porosity, these kind of parameters, or some of the fluid properties. Then you use this simulation to have basically how the evolution in time of, say, pressure field, saturation, phase saturation field, etc., but also what we are able to observe from the well location. Of course, you can observe some of these from, or some low resolution changes in here using geophysical monitoring schemes. But for the most part, what we continuously observe are observations from the wells. And these are some examples of these observations. Right? This is what we call the prediction problem, the forward problem. The inverse problem is the opposite. Given that data that you have observed, how can we reconstruct this model? And of course, this reconstruction has to take into account also a lot of other data that was collected and used to build this model. So if there's a geologist that is working with you, if they have a conceptual model of that geology, you have to be able to honor that when you're updating this, right? And that's one of the challenges that we have. So I'll go through a list of challenges, but one of them is being able to keep the geologist happy. So one of the main challenges that I said when you work in subsurface is uncertainty and non-uniqueness. And the source of that, there are several sources for that uncertainty. The main one is subsurface description itself, basically the geological model, the property distribution, etc. We also have noises in our measurements. That could be another source for uncertainty. And also modeling errors. And that depends on the application. So if you look at conventional reservoirs, and that refers to imperfect physics. If you look at conventional reservoirs, we have a rich literature and 100 years of research going into understanding how those systems behave. When you look at fractured system in unconventional reservoir, you can't trust the physics that much because it's very complex and we haven't studied that for a long time. So this modeling error can be very small or can be very large depending on what you're dealing with. But for us in this presentation, mainly we're focusing on the geological model and the uncertainty that we have in that description. The second challenge, as I mentioned, was a constraint or geological plausibility that we need to adhere to. We have multi-scale heterogeneity. Geologists may have a particular form of correlation structures that they may want to enforce, but you can't just update this model as you wish. You have to make sure you remain consistent with the original assumption about the patterns or geological features that you have in the field, unless somehow you can work with the geologists to revise their understanding of what is happening. And then there are complex spatial patterns. Mathematically, these are very difficult. You may look at some of these fluvial systems. They're very simple when you look at them. Mathematically, they're extremely difficult to describe and even more difficult to update, right? If you want to stay realistic in terms of plausibility of the, and everything we do here at the end is going to be based on numerical analysis. So we have to somehow automatically be able to have some automatic description, mathematical description that allows us to change that in a way that's consistent. And that's not easy. So the third challenge is nonlinearity in computation. And in our lab, we do a lot of simulation work, and we have to have our own dedicated computer clusters in order to be able to actually do this kind of simulation. Sometimes when you're dealing with coupled physics systems, geomechanics and flow together, these can take a while to run. And that's, you need extensive computational resources in order to deal with this kind of problem. And the last one, which is really what I'm going to focus on next, is dimensionality and resolution. These models are typically high dimensional with high resolution. The data that we have, the content is really very limited. But still, there is information there that can allow you to update these models. And we want to see how we can proceed with that. So here's an example. You're looking at some outcrops, and I'm just taking one example, one layer of our model, to show you how detailed heterogeneity can be in your original description. But you may have to sacrifice in your update scheme, you may have to sacrifice some of the details so that you can actually effectively update larger scale patterns. Why do we want to do that? Because these larger scale patterns, for the most part, they're the ones that have first order effect on the prediction of the slope. This is an example of a low dimensional representation, but it's from 1970. And if you show that to a geologist, they're not going to like it, right? But this was 1970, and today I'm talking about deep learning. So we have made a lot of progress, and along the way, we have developed many approaches to deal with this problem. Low dimensional representation of a very detailed model in a way that you preserve the major connectivities that you have. The reason we are able to do that, and the premise of this, is because geology is continuous. And that continuity means a spatial correlation. A spatial correlation translates to redundancy. If you're doing image processing, as soon as you see an image, you know that image is compressible or not, depending on the correlation you see in that image. So let me just tell you what some of the traditional way of dealing with this problem. Mathematically, and I don't want to go into the detail, just use the picture to explain it. Mathematically, what we want to ideally do is, instead of dealing with pixel values, which is what we do when we build this model, we actually assign property to pixel values. But when we want to update this model, we have to move away from that, because those descriptions are too detailed, and updating them is quite a challenge. So the way we want to handle that is, at least one approach, is through the basis expansion, right? A linear expansion in this case, where we actually need to come up with these kind of what we call basis images. And those basis images, I'll explain, there are two ways you can go about this, but those basis images have weights in front of them. Now, those weights will become your new unknown instead of those pixel values that you have. Now, all of the spatial correlations are captured in those basis elements, and you don't have to deal with them. They're fixed. But then you have to adjust these weights in order to update this solution. And these weights are low dimensional now. Why are they low dimensional? Because there, as I said, there are special correlation you can exploit to have these kind of effective basic elements that lead to low dimensional representation. Let me actually expand on that. Here is a JPEG compression. Everybody knows JPEG, right? So here's approximately how it works. These are two different examples. One of them is showing a turbidite system. The other one is kind of a shallow near offshore environment. So basically what you're seeing is if I transform this and take it to frequency domain, right? This is exactly the same representation in different domains. But what happens is that you see these blue regions, those are coefficients that are either 0 or negligible. If you drop 99% of these coefficients and keep only 1% leading ones, that would be the approximation to this image, which is capturing the large scale variability. Of course, the details are lost. The same thing in here, you can see that you can even become more aggressive if you don't have as much detail in your image. So what are the basis functions for these? What are those images for this example? Those are just cosine harmonics of cosine functions. Image processing tool, very commonly used, and we have it in our day-to-day kind of, when you take a photo, if you want to compress it, use one of the standards, JPEG. But that's not enough. For us, when we deal with a particular application, just looking at harmonics of cosine is not going to be as efficient. For example, if you want to compress an image of a face, you want those basis images to have features of face in them, right? So when you're dealing with a fluvial system in our models, we want these basis elements to be adapted to those features that we have in our models, the fluvial patterns, right? And that's, you can do this, and you can do this with principal component analysis. Those of you who might be familiar with that, you can get what we call eigenspacing. It's a traditional approach. That's not what I want to focus on. What I want to tell you is that this key word here, this is data-driven now. You're adapting your representation to the actual data that you have and hoping that the features that you keep in your representation would be more meaningful. Okay? Now I'm going to switch to neural network and basically tell you why this is such a flexible and powerful way to generate data-driven low-dimensional representation. And so the inspiration here, the neural networks, for those of you, everybody nowadays have heard of neural networks, they're inspired by the information processing of our brain. They're designed to detect, extract patterns, and use them for prediction. That's what they do. You have a lot of training data. They take that training data. There are a set of weights that they will be adjusted during the training to learn those patterns. And once they learn that, they're able to use those patterns to make predictions. Very simple way of putting it. Now, very briefly, I want to mention the main elements in a neural network model. You have an input layer, you have an output layer, and you have some hidden layers in between. And there are connections between each subsequent layer. And the connections have the weights that you're trying to train so that they learn the kind of data, the features in the data that you provide as input. Now, the operations are pretty simple. The operation pretty much is going to be the linear combination of these weights between subsequent layers, followed by what we call an activation function. The purpose of this activation function is basically to say, for a neuron, based on a given input, whether it's going to be activated or not, depending on the input that you have. And that creates basically a nonlinearity, that adds a nonlinearity to your representation, to your approximation, which is essential if you are dealing with complex data. And then finally, the training process for this is you have a large data set that you provide to this network as input. Depending on your application, you want the output to be some sort of a prediction, and you have the prediction for that data set as well. So you let this network to learn that relationship, adjust these ways to learn that input-output relationship. So how are we going to use this? The version of this that I'm going to talk about and show some example is convolutional neural networks. The convolutional neural networks are very efficient. They're a special type of neural networks, very efficient for images. Images are high dimensional. So if you want to connect every pixel to the next layer, you're going to have a gigantic network. And that's not easy to handle. A more efficient way is really to take advantage of spatial correlation in images. And the way to do that, an efficient way to do that is through convolution. Convolution with filters. Now we're going to train filters to adapt filters to the spatial correlation between those images. So the process or the elements in a convolutional neural network is basically a convolution operation. These filters are unknown, meaning they're the weights that we want to train, updates during training. They basically scan your input images and try to summarize the features that you have in the images. Then we have the same kind of nonlinear activation function that we apply to the output of each layer before we go to the next layer. And finally, in order to reduce dimensionality, there's this process of max coding, can think of it summarizing the features that are learned in different layers. Now, if I want to expand and show you one example of such a network, here is an example where we use classification. There are 6 different geological scenarios with fluvial systems in different directions. What we want to do, we want to provide an input image and see which class it belongs to, right? But this is basically a training network to do that. During training, we provide, let's say, 1,000 or 10,000 of these images, and we tell the network which class they belong to. So during training, this network, by adapting those filters, will learn basically the correspondence between an input image and the class it belongs to. This is a very simple example, very commonly used. Okay. Now, what we're going to take advantage of for dimensionality reduction is this particular architecture known as autoencoder. What's the purpose of an autoencoder? The autoencoder architectures, they basically start with a high dimensional image. The purpose is to use convolutional neural network to actually map this high dimensional image to a low dimensional, what we call latent space. The latent space, the feature it has is that you have very few parameters in the latent space that control the spatial distribution of these patterns. And if you change those, you will see significant changes in these models. So the importance of this is if I'm trying to solve an inverse problem, I want to do it in the latent space. I don't want to do it in the original space. Because I don't want to deal with this complexity. I want to go to a low dimensional space that has computationally more efficiency. But more importantly, these layers have learned what kind of feature I'm after. So if I make changes, those changes are not going to be arbitrary. Those changes are going to be based on the patterns that are learned in this network. Now, on the other side of this is a decoder. What's the job of the decoder is that any change I make in the latent space will be mapped onto the original, back to the original of data domain, in this case, the high dimensional image. This whole network together is trained jointly using data that we have. Let's say if I use statistical techniques to generate 1,000 of these models, I can use them to actually train a network like this. So once I'm done with this training, if I want to go to the low dimensional space, I basically take the encoder part of it and use that part after training. If I want to go from low dimensional space back to the original domain, I use the decoder side, which is what we do in our inverse problem. Because in inverse problem, we're going to make changes here, and we want to see what those changes mean in the original domain. Anyway, so with this introduction, I'll basically show examples to make the case why these are so flexible and powerful in learning spatial patterns and using a low dimensional representation to describe them. So, and the key features are dimensionality reduction, preserving main geological features, and efficient workflow in the low dimensional. I'm not going to talk about it in this presentation. Once you go to this domain, there's a lot of interesting things that we can do. I can begin to think about can I describe the dynamics in that low-dimensional space? And these are some of the research activities that we're working on at the end of my talk. Tell you a little bit about those. But for today, what I'm going to talk about is that I can update larger scale models in a low-dimensional latent space by changing the variable in that space. In fact, if I want, I can actually have a latent space, a low-dimensional latent space for my model parameters. I can actually have latent space for my response data as well. Maybe for this kind of time series data that we have as well outputs, it may not be that big of a deal. When you go to 4D seismic, that becomes important because 4D seismic is going to have also very high dimensional spatial images that we need to deal with for data integration. Then you may want to look into low dimensional representation for those kinds of monitoring data as well. And finally, if I have a low dimensional representation for model parameter, a low dimensional representation for my data, I can do my inversion in the low dimensional space, which means during training, I will try to create a mapping between the two low dimensional spaces that are identified during training. So I can actually use this low dimensional representation for prediction, which means going from parameters to data, or I can use it for inverse mapping, which is going from data to parameters. All of that can be formulated and training can be used to enable that, right? Depending on what your purpose is. We mainly use this in order to generate proxy models, very efficient, fast prediction models that, let's say if I want to do uncertainty quantification, I may have to run 10,000 of these simulations, but I don't want to pay the cost of full simulation. I may be able to do these kind of schemes to have very fast prediction. And this is, of course, the part that we use for inverse modeling. So originally, if I wanted to deal with this problem, this was my data, this was my the parameter field that I want to update. But with these kind of representation, I first map them into their corresponding latency space, both the data and the model parameter. Then I will try to establish the relationship between them. Once I use this mapping in the latency space and I update the latent parameters, then I can use the decoder side of my representation. Then I use the decoder side of the representation and take the updated latent variables, map them back to the original domain, which will give me the updated model. So let's take a look at a couple of examples. This is what they call a Gaussian model. The spatial distribution is called the multi-Gaussian distribution. These are 5 different geological scenarios. We use training data from all 5 scenarios, but the reference case basically belongs to one of these. So the idea is, if you actually train the network with these data, can we actually have a good mapping of what this reference model would look like? A more complex example would be the fluvial channel. Of course, everything in here is 2D, but these are starting examples. We have examples where we look at 3D models with real complexity. Again, in here, you will see 5 different scenarios, but this feature only is from one of the scenarios. We want to see, can we use dynamic data to actually recover something like this? So the results, these are 3 different examples. I'm showing the reference cases, and on the right side, I'm showing the estimated cases from these networks, right? From this latent space, what we call latent space inversion. And then these are the fluvial examples where you do have, these are the well configurations in each case. These are 3 different reference cases and the corresponding solution. This reconstruction is basically based on the information, dynamic information that you see from those 4 wells. So we don't expect them to have a perfect match because the data content is limited, but you can see the larger scale patterns are consistently identified. When I say consistency, it's not just how close they are to this solution, it's the fact that the solution looks like a channel. And that's very important because it's not trivial to update these channels automatically, mathematically, and still do not disrupt the connectivity in the channels. That's not a trivial problem. So the fact that you still see some connectivity patterns that look like fluvial channels is quite promising. Here's another example based on the Volve model from North Sea data set, where basically we use 3 different scenarios in order to train these kind of networks. And this is basically showing a reference case and the inverted case using this autoencoder architecture that we have established. And we see very good correspondence between what we have as reference and estimated skill. So what are other examples? We have used this kind of architectures to deal with uncertainty in geological scenario. I showed a couple of examples, but you can actually do that. So what this slide is showing is that all the data that you have, if you combine that data, there's a lot of uncertainty still remaining. So we typically use geostatistical simulation to deal with the uncertainty that you have in your representation of the geological models. So we actually developed, so if you take these kind of representation and look at them in the latent space, what you see is that there's a nice clustering of these examples that have different spatial patterns in them in the latent space. What that allows us to do is basically take this type of clustering scheme and implement a 2-step procedure. First, we actually use this scheme to resolve the uncertainty in geological scenario, which means what are the directionality of these patterns, right? Are they north, south, east, west, diagonal? Then once that is resolved, then we actually go after conditioning them to the dynamic data. This is basically from a paper that we recently published where we're basically using the data that we have to generate multiple geological scenarios, and we go through 2 steps. The first step is identify geological scenario. Which of those scenarios are supported by the dynamic data? Once you do that, then you actually generate conditional realizations that belong to that scenario that you have identified. So here's an example showing for the Volve model with fluvial patterns in it. So we actually use those latent space representation to come up with this as a solution. When you project that into this latent space representation for classification, based on where it falls, you're going to explore that area to generate conditional realization. And that's basically showing the likelihood of different scenarios that we have. And obviously the meandering channel in this example has the highest weight in that classification. Another example, very briefly, the data assimilation, ensemble-based data assimilation has been very popular in dynamic data integration. And what I want to just briefly show here is that this is a very recent work that we are actually going to do the entire data assimilation procedure performed in the latent space. All we have to do is identify what these latent spaces are, which is what we do here in training. Once you have that, then you can actually implement this kind of data assimilation scheme all in the low-dimensional subspace. And these are some examples showing what you see in here is are some of the prior realization. We've got a posterior realization. It's a probabilistic framework. And what you see, these are the responses before data integration and after data integration. The gray shows before data integration, and the colored ones show after data integration, which shows better match to the data. So, okay, let me now briefly conclude. So, the flow properties that dominate the response of subsurface flow systems have a strong spatial correlation with that. What that means is that they are amenable to low-rank representation. There are classical techniques to do that, but more recent data-driven techniques based on deep learning offer very powerful low-rank representation. Not just low-rank representation to represent those static images, but also a latent space representation that provides other capabilities, including prediction in those spaces and data integration in those spaces. And of course, I showed examples from direct inverse mapping, where in the latent space, where you basically try to connect the latent space of data and models and use that for inverse mapping. And then finally, these deep learning architectures are showing promise for deployment for various applications, including proxy model development, data integration, optimization framework, and in general, any prediction problem in the subsurface. Now, with that, a couple of slides on basically the general research area, some of the other projects that we work on. So I showed some slides about uncertainty in the conceptual geological model. This is a key problem for us to deal with, which means that you want to bring geologists' uncertainty into dynamic data integration and work with geologists and the scenarios that they have uncertainty about to see whether we can reduce those uncertainties. I showed examples from pattern-based representation using deep learning models, which was the topic of today's presentation. And I showed examples from ensemble-based data assimilation. And in some applications, we are looking at coupled physics models, integration of multi-physics data into these models. In field development optimization, we also try to develop a stochastic optimization techniques that can account for uncertainty in the geological representation. For CO2 storage, we are working on a DOE project right now. In fact, a couple of DOE projects, one of them finished recently. But the idea here is that to basically formulate optimization problems that can handle prediction uncertainty as well as risks of leakage or deformation in this system. And in terms of data science application, we have projects in geothermal system looking at dynamic neural networks or recurrence neural networks, trying to predict the behavior, short-term and long-term response of this system, both for geothermal reservoirs and the power plant, the surface system. And we had a recent project by CRC, supported by CRC, where we looked at a very complex field in LA Basin to develop neural network models to manage their water flooding operation. And also currently we have a large project with Aramco focusing on developing deep learning techniques for unconventional reservoirs. So in terms of future direction, the general theme of the research in our lab is going to remain subsurface flow systems, and the two technologies that we're going to focus on and leverage them, data science and system science. The application, conventional reservoirs, unconventional reservoirs, geothermal reservoirs, and we are going to expand in this direction quite significantly in the next few years, of course, as well as geothermal. And one of the research directions that seems to be picking up in the future is dealing with multi-physics systems, because more and more of these energy systems involve coupled flow and geomechanics. And in order to be able to do effective data integration, you need to represent both physics in a coupled way. And those are some of the areas that I collaborate with colleagues who are expert in geomechanical, coupled flow geomechanical modeling to develop a scheme for optimization and inverse modeling. And unconventional data-driven techniques are going to be very effective for unconventional reservoir just because the physics is so uncertain. We don't know the physics very well. So, and we have a ton of data that's based on the recent development in the past 10 years. The factory site development that we have for unconventional, there's an abundant data out there that can be leveraged for that purpose. And I talked about geothermal reservoirs, some of the challenges there. We're developing data science tools for short-term, long-term prediction. And we're now looking into physics-constrained data-driven techniques for these systems. And the idea there is that developing prediction models that can be used to sustain their production through optimization techniques. And I talked about the geologic CO2 storage, which is an area that we're going to stand up. At the end, I want to acknowledge the sponsors in the past 5-6 years that have supported us, our lab. Our lab is multi-sponsored by both government agencies and the industry, as well as foundation, the Particular Energy Conservation Foundation, for being very generous to us. And this is a picture a couple of years ago from my lab. With that, I want to thank you for your attention and open the floor for any questions you might have.
Great, thank you. Good. Well, we do want to leave time for questions, and we'll take some inside and from online. I think I want to lead off with a question, though, and that is, in earth sciences, we often have a bimodal distribution of people. We have people who love math and physics and computer science and coding up, and maybe the challenges there, try to get them outside once in a while to see the real world, right? In fact, sometimes I have to schedule my research seminar in a park just to get people out looking around, sunshine and fresh air. The other side are very smart people who are out in the real world collecting data, samples, mapping, so forth, bringing them back to the lab. They don't want to be computer scientists. They don't want to, necessarily be the ones coding up these tools, but they do want to use the most modern data analysis techniques on their data possible, like neural nets, machine learning, etc. So let's say you have a group of those people, undergrads or grad students, and you want to teach them these quantitative methods, but you don't, they don't want to be the ones writing the code. They just want to become super users and be very fluent at using the tools. How would you approach teaching?
In fact, I do have a
course like
students, both types of students in my lab right now. So I do have petroleum geologists in my lab who, when they come in the lab, they don't have that much quantitative skills.
Mm-hmm.
And I do have electrical engineers in my lab who all they do is estimation control and this type of problems. So what I try to do is try to kind of have them work together in a way that each of them will bring their contribution, learn a little bit from the other side. It can't be just hands off. Yeah, there has to be some integration, but it doesn't mean they have to learn all the numerical skills that the other side have. But they need to know enough to contribute effectively to the project. For example, what I was showing you here was geological scenarios. Who comes up with that? Not an electrical engineer, a geologist. They have to sit there and say, what is realistic for a fluvial system, what is not? I can't do that. I'm not a geologist. I work on subsurface flow systems, not on the geology side, but on modeling side for prediction, optimization, inversion. I have to understand geologists and their concerns. I have to work with them. But those geologists provide the input how to generate these models, these data sets. And of course, they need to learn to operate those tools so that if they need to train based on those, they have, and that's not really that complicated and that involved to use those tools. To develop them is a different story. Mm-hmm. So you have to basically see where they can contribute most effectively and tap into that. My most productive PhD student right now is a petroleum geologist. He had about 5-6 years of experience coming to the lab. I was very hesitant at the beginning because I knew these are quantitative, this kind of work, they require, most of this work that you see, by the way, from his work. But he was interested to learn. He didn't want to be hands-off. He actually took courses in machine learning, 1 or 2 courses, but he was very independent, hardworking PhD student. And he's probably finished next May, but up to now, he's had 7 journal publications in the past 4 years, which is quite productive.
Yeah, so maybe teaching via projects for those people.
Yeah, and then the way it works, I have group meetings every week with my lab, and they learn about these things. They don't need to learn about the details, but they understand what the other students are doing. And if they need help, they go to them, to me. We have, smaller project meetings, and those things can be transferred, but not at the level that the other guys do.
Sure. Question? Yeah.
I have a question. Do you have any experience with carbonate reservoirs? Have you worked on any carbonate systems where it was strictly that plastic?
Not really. No, I haven't. Yeah, I haven't used carbonate reservoirs. Most of my effort has been really on fluvial systems. There's a reason for that. If you look at the literature on dynamic data integration, these are very challenging to do. There's this fluvial pattern. Now, if you go to fractured systems, that's a totally different story. They have a lot of complexity too.
Well, I was thinking of carbonates of the dynamic over. That adds a lot of complexity as it goes into the subsurface. So I was just curious if we had any experience.
Right. No. I think what we have worked on, not carbonate, but naturally fractured reservoirs, and there we cannot hope to have this low content dynamic data to recover a small scale fracture. But what we can hope for is characterized fracture density in different regions, depending on the flow response, right? But very limited exposure to that, not much.
Good question. I've worked a ton on carbonates too. They're way more complicated.
Right.
And 60% of the reservoirs in the world are carbonates. So, yeah. Okay.
Well, similar in the geothermal, I think you've been working basement range where there's not a magnetic source. So you need the permeability ellipsoid is extremely anisotropic. So in those cases, you have kind of a single conduit essentially. So how successful have these inverse methods been characterizing that kind of permeability?
So for geothermal reservoir, most of the things we've done is really looking into microseismic response and try to see whether we can map that to with permeability distribution. But what we have done is most of it on that ellipsoid that you're talking about, we have tried to give some uncertainty to that ellipsoid, which means the correlation structures could go in any direction, and see whether the flow data shows any sensitivity to limit that description. And depending on the content of the data, yes, sometimes you can do that. But the way we have looked at it is we divide that ellipsoid into, say, 12 different directions, 12 different scenarios, and try to see which one can be supported by dynamic data. That's the kind of work that we have done in that domain.
Turbidites are highly anisotropic too, the flow, so that's a good issue there. Oh yes, go ahead, Hijra.
I want to ask you what are the advantages or benefits of this neural network to model space in comparison to other conventional ways, like wavelets or wavelets?
Good question. Very good question. So I think I do have some backup the slide if not sure. So let me go back to that Fourier domain representation.
We're going to take some questions from online too, so
Sure.
if you could keep it brief.
Okay, just. Okay, so the wavelets are JPEG 2000. This is JPEG. That's basically the upgraded version of JPEG, right? Because what the wavelets do is they give you localization, multi-resolution. Proof that needs low. I had a slide that I skipped it. I don't want to spend too much time on this. The problem with wavelets is that if you have data, geologic data, you want your dimensionality reduction to be adapted to that. Wavelets and DCT type compression techniques are generic. So these wavelets have nothing about geology. So if you want to customize them to represent geology, then these are not good. If you want to compress any image you take, they're very effective because they don't make any assumption about what image it is. And they're very generic in that sense. But I have a couple of papers on wavelets, quite a few papers on this JPEG, and there's a lot of discussion in those papers, advantages and downsides of using those.
I think we have other tools that have already been developed, like wavelets or to describe geological formation.
What I'm familiar with, you probably know about sidelets, yes, right? Sidelets are, but the idea there is that you still have a generic representation to represent those curves that you see in seismic data. It's not a specific training data. And when you go to sidelet and wavelet, there's just one filter that is operating. When you go to these techniques, the deep learning techniques, you have many filters. That makes them very powerful because they learn different features without interfering. The filters interfere with each other.
Do you need to change the coefficients?
The coefficients are, during training, they are being adapted to the data.
You don't need to check that.
If you have evidence that new data comes in and some new features are, you have to retrain that.
Yeah, we could talk a lot about that one. That's the question. I'm just going to check online. Solo, are there questions online?
Can you hear me? I don't think they can hear me.
Slow Mac may have some problem.
Oh,
I
okay.
don't see any.
You don't see any questions online?
Yeah.
Okay.
Uh,
One in the chat, maybe?
that's the slowest message.
Okay,
So
that should have
talk
issue.
about people that give questions.
Okay. Go ahead, Ming, you've got a question? Yeah.
Yeah, so when you mentioned trying to use this latent layer of the training feature to help reduce the uncertainty of the geological uncertainty, I'm wondering, because when we have this geological uncertainty, also because when geologists are dealing with the data, or geophysicists dealing with the data, they have certain limitations. But this latent, because it's very high level summary of this feature, by summary so many kind of the data together, it will get some other type of uncertainty. It feels like you are using one type of uncertainty to replace the other type of uncertainty. How, when they conflict, how you decide?
So the way we formulate the problem, in this case, you're right, in the sense that we're focusing on a spatial representation. Now, if the geologist has uncertainty about the structure, that can't be handled here. There are ways to handle that, but not in the convolutional neural network framework, because I'm particularly focusing on images, not the structure, right? So if there are other sources of uncertainty, you can potentially come up with a neural network representation that would handle that, but not the one that I showed, because these are based on convolutional operations, right? And convolutional operation is not effective for capturing uncertainty in the structure. Or let's say if you have a fault system and you don't know exact location of the faults, this is not the right way to go. But you can sit down and think about how to address that using this kind of architecture.
So you're very selective on what type of data you can deal with to have to reduce that.
This is mainly about images of properties, because they basically dominate the flow response. This doesn't mean other things don't dominate the flow response, but this is one.
Okay. Yeah, maybe later.
Yeah, maybe we'll
we can
wrap
chat
it up.
offline if you-
Just, and anyway, immediately following this is the student lunch, so you can sit in on that. You have a class, okay. All right, well, I think we'll let it go at that, but you can always catch up
You can
in
send
other
me an
ways.
email.
Yeah, in other
Yeah,
ways.
definitely.
So yeah, right after this, there'll be the undergrad and grad student lunch with Dr. Jaffarpour, and then meetings and stuff. And just a reminder, everybody, oh, excuse me, just for a sec. Just as we wrap up, if you can remember to send your feedback by the end of tomorrow, that would be great. So let's thank Dr. Jaffarpour.
Thank you.
Recording.